Hello and welcome. Today's Thursday, June 25th. Welcome to this virtual AI Huddle. I'm honored to be joined by Chris Deotte and Abhishek Thakur for this Accelerator Power Hour. My name is Yufeng Guo, and I am really excited for the next 60 minutes. Hope you are too. So let's move over and meet our excellent presenters. Here's Chris and Abhishek themselves. How are you guys doing today?
We're doing great. I'm doing great.
I'm doing fine, thank you very much.
Hopefully everybody, everybody can hear us okay. I see everyone's introducing where they're from all over the world, just about every continent other than Antarctica. Absolutely amazing. Great to have everybody on. So what we'll be doing is, first up, Chris will be telling us about how to compete in a Kaggle competition using TensorFlow GPUs, and he'll be using the Bengali Handwriting Classification competition. Chris Deotte is a three-time Kaggle Grandmaster and data scientist at NVIDIA. He's earned a BA in math and has worked as a graphics artist, photographer, carpenter, and teacher. What an amazing career. He went on to earn a PhD in computational science and mathematics. Look at him go. So then in the second half, we're gonna have Abhishek giving us a rundown on his approach to deep learning using PyTorch and TPUs. And so he'll be showing us how to harness the power of TPUs and PyTorch to make almost any model train super fast. And Abhishek is the world's first four-time grandmaster. He works as a data scientist, and when he's not caggling, working, or ranting, you can find him teaching applied machine learning on his YouTube channel. So you can check that out. It's in the description below. And currently, he's also writing a book titled Approach Almost Any Machine Learning Problem. So please, I guess, give a warm virtual round of applause for our presenters. And yeah, with that, I guess we'll let Chris get started. He'll go into his presentation, and Abhishek will have you come back for the second half, and we'll chat with you then.
Sure, see you in 30
Sounds
minutes.
good. All right, Chris, let's have you go into your presentation. Great.
Wonderful. Well, welcome again, everybody, to the Accelerator Power Hour with Kaggle Grandmasters. My name is Chris Deotte. Today I'll be talking about using GPUs in Kaggle competitions. So I'm told there's over thousands of people here, and I have to say this is the largest classroom I've ever taught. It might take me a while to learn all of your names. Here's the diagram I use for all of my Kaggle competitions. The two most important things are setting up a reliable validation scheme and doing fast experiments. This is why accelerators are so important. If you use a GPU instead of a CPU, you can do 10 to 100 times more experiments. That means you'll win 10 to 100 times more gold medals. People frequently ask me, how do I increase my leaderboard score? Answer, experiment. Try more ideas. Here are the 5 areas you can experiment with. 1, try different pre-process and feature engineering. 2, try different data augmentation and external data sets. 3, try different model architecture and loss. 4, try different training schedules and optimizers. 5, try different post-process. Today, we're going to practice these techniques by working through an image classification task. Kaggle held a competition a few months ago to classify Bengali handwriting. We were given a grapheme, and we had to build a model which would identify which of the 168 grapheme roots was present, which of the 11 vowel diacritics was present, and which of the 7 consonant diacritics was present. We'll be working through a Jupyter notebook together for my team's 4th place gold medal solution. Let's get started. All right, so the first thing we're going to do is we're going to load the libraries. And you can see that today we'll be using TensorFlow. Next, we're going to initialize the GPUs. Now, this is a great thing about TensorFlow. TensorFlow, if you have one GPU or many GPUs, TensorFlow will automatically use all your GPUs. It'll take care of communication and multiple training for you. Next, we're going to enable mixed precision. If you have a recent GPU, using mixed precision can speed up your GPU as much as 2 times, and it can allow your GPU to store as much as 2 times as much data in RAM. And next, we're going to initialize a log file. So for every experiment, you're going to want to record which pre-process, which data augmentation you used, which model and loss, which learning schedule and optimizer, and which post-process. You're going to want to write that to a file and also save what the validation score was. So you'll have a record of all your experiments. Okay, so the first area of experimentation is pre-process. So in this competition, Kaggle provided Parquet files, and the images are sized 137 by 236, and the pixel values are between 0 and 255. So what we're going to do is we're going to load in these parquets, and we're going to resize the images to 64 by 64, and we're going to normalize the pixels from 0 to 1. So note, this is our first choice in our experiment. If we were to do a different resizing or a different normalization, this would affect how accurate our model is later on. We see that we've loaded in 50,000 images, and now they're size 64, 64, and color 1. So for this notebook, for this demonstration today, we're only loading in a quarter of the images so that the notebook runs faster. And let's go ahead and display the images to make sure that they were resized correctly. So you can see here, here's some examples of the Bengali graphemes, and we can see they look right. And then let's look at some of the labels. So we see here that the first image, which is up here in the top left, that first image has grapheme root number 15, vowel diacritic number 9, and consonant diacritic number 5. So that's one of our 50,000 training images. All right, the next area of experimentation is data augmentation. So we're going to be performing our data augmentation inside a data loader. Now, it's very, very important that we optimize our data loader for GPU speed. So when the GPU is training on one batch, our data loader in the CPU will be creating the next batch. So it's very important that the data loader can make a batch faster than the GPU can train on a batch. The main thing to consider when you're trying to optimize GPUs for speed is GPUs can do a tremendous amount of work at a fantastic speed. So we always want them working. That's why it's really important that your data loader provides the images fast enough, because we don't want the GPU sitting around not doing anything. Furthermore, it's good to consider increasing your batch size as large as it goes to force the GPU to do as much work as it can. When your model's training, if you look at a monitor of your GPU usage, you should see it working at 100%. Now, a common mistake people make is they try to resize their images inside their data loader. Notice that was step 1, pre-process. Anything that we're only going to do once, we do that once and get that out of the way. We're going to be building our data loader using a Keras sequence. Notice that we'll be doing for our augmentation, we'll be using cut mix augmentation, and we'll also be doing rotations, scaling, shift, and coarse dropout. So let's go ahead and look at our data augmentation and make sure it looks correct. Whoa, that looks weird. Let me explain what's happening. So we want to make sure our data augmentation is doing what we want it to do. So we're using cut mix. So cut mix is actually mixing two images together, but it's hard for us to visualize and see if it's working correctly. So what I've done here is I have this debug flag, yellow equals true, and what it's doing is it's turning the first image to completely yellow. So right here we can see that, so you can see there was the first image, and then cut mix removed a piece of it, and then the blue is the second image. So we can actually see that cut mix is working correctly. It's taking out big rectangles and putting in a second image. Furthermore, you can see down here that the image was rotated and shifted. In this picture right here, you can see all the coarse dropouts. That's where we just remove sections of the image. So if we take off this yellow debugging, we can see, so these are the images that our model is seeing. So each time it's random, and each time the data augmentation will do different augmentation. So deep learning models need lots of examples to train with. So data augmentation is very important because now instead of having 50,000 images, we're essentially making as many more images as we want. All right, the next area of experimentation is our model choice. So we're going to be using transfer learning. In the last 5 years, convolutional neural networks have begun to classify images better than humans. And listed, and in this picture here, you can see names of many of the state-of-the-art image architectures. You see EfficientNet, you see DenseNet, you see SENet. So what's great is we don't have to build these networks from scratch. We can just download them from the internet. And furthermore, we can also download them and have them pre-trained on tens of millions of ImageNet images. This means we can download a model and it already has some intelligence. In this plot here, so there's many models to choose from. We're going to pick a model up here in the top left. It's EfficientNet B4. So we notice that the number of parameters are small and the accuracy on the ImageNet task is very high. So with the parameters being small, this means it's going to train very fast and it's going to achieve a high accuracy. Now, how we do this in the code is very easy. In TensorFlow, it's just one line of code. This is it. We just call EfficientNet B4 and TensorFlow downloads it from the internet. And then furthermore, we're saying to use the pre-trained ImageNet weights. Also, we're not going to include a top because we'll be building our own top to the model for our specific task. So our top is going to output 3 different numbers, one number for the graphene root, one number for the vowel diacritic, and one number for the consonant diacritic. We also make sure that the output type is float 32 because if you remember, we're using mixed precision inside our model and we don't want the float 16 to come out. Additionally, we're going to be using cross entropy loss. This is just softmax followed with a cross entropy. We're going to be using the atom optimizer, and we're going to adjust how much attention the model gives to each of the different tasks. We're actually going to have it put 1.5 weight emphasis on getting the graphene root correct and 1 on the others. So we're using transfer learning. You see how easy that is to do. Maybe someday they'll have transfer learning for humans. Then we won't have to attend to this data science conference. We can just download it from the internet and we'll immediately know this stuff. And then we would be using transfer learning to learn about transfer learning. Okay, so we could have our model output a metric, but the competition metric is macro recall, which is not included in the Terrace metrics. So we're gonna calculate this metric ourselves, and at the end of each epoch, we're gonna display that metric. Furthermore, we're gonna write it to the log file to keep a record of it. And we're also going to, if our model gets more accurate after an epoch, we're going to save the model weights also to the disk. So everything is going to be logged. And let's go ahead and run these. The next area of experimentation is the training schedule. So this is the training schedule we're going to use. The x-axis is the epoch. The y-axis is the learning rate. So if you remember, our model already had some intelligence. So we're going to slowly introduce it to the new images. So we'll start the learning rate at 0. And in the first 5 epochs, we're going to increase the learning rate to 0.001. We'll then keep that constant for 10 epochs. And then we're going to decrease it by 75%. And we'll continue to go down in a stepwise fashion like this. I found that these step decays work very good. All right, let's go ahead and start training our model. So training a model is super easy. All we do is first, we build the model. We do it inside a strategy scope. So this is what we set up earlier with TensorFlow. This is where TensorFlow was going to go ahead, and if we have one GPU or multiple GPUs, it's going to take care of all that for us. Next, for our data, our data will be produced by our data generator. We then create that custom callback, which is calculating our metric and recording everything to the log file. And then lastly, all we do is we just call model fit. And we see below that the model is learning here. And this shows the progress. So today we're training on an NVIDIA GPU V100. We'll see that each epoch will be about 20 seconds. We just got the first result back. So currently our validation is 0.05. So our leader score is 0.05. Not too good yet. So let's go ahead and we're going to train this for more rounds. But let's just summarize what we've done so far. So what we're looking at here is a single experiment, right? We chose a pre-process, we chose data augmentation, we chose a model and loss, and we chose a learning schedule. And now we're training this experiment and we're seeing an output of what the validation is. And if you remember, since we have a reliable validation, this score we see, if we submit this, this will be our leaderboard score. So you see, we can now, and all of this experiment is being saved to the disk. So you can see we can run many experiments and we can now find the most accurate model. All right, so we're going to let this train for a number of epochs. It's gonna take some minutes. So let's go ahead and ask the audience if they have any questions.
Yeah, let's do it. So we've got a couple of questions from the Q&A, and let's see if there's some from the live stream. I think the first one that we can talk about is some folks are asking why cut mix makes sense. You know.
Okay, so the first question is why cut mix. So here's the idea. There's many different augmentations. So this is a very important question. Which augmentation do you use? You're specifically asking why cut mix. So my general rule is you choose augmentation to try to make images that look somewhat realistic. So in this case, you know, we have a typical graphene. It has different pieces. It has a root and consonant. So by taking pieces of one graphene and mixing with pieces of other graphene, it's essentially we're making new graphenes that somewhat look realistic. So it very much is appropriate, and as you've seen if you participate in this challenge, it's very awesome. Effective.
So you kind of found this a little bit empirically, like you probably tried a few different approaches as well.
Yes, exactly, and that's what you'll need to do in all these competitions. It's a lot of trial and error. But you have some direction. If you read the forums and you look at public notebooks, people will start to discuss what works. So in this competition, for instance, everybody was saying that cut mix works very good, cut out works very good. So that encourages us to go ahead and try these for ourselves.
There's another question in the kind of Q&A about see, why did you need to use loss underscore weights? I'm not sure. Are they just referring, what part of the code they're referring to there?
Okay, you're probably referring maybe to what we did here. Yes. So again, this is an optional thing. You don't have to use loss underscore weight by default. So basically, our model here, it has 3 outputs, right? It's outputting 3 different things. So if we don't include this, then each output will be trained equally. But what you do is we actually are going to say we want to apply, more backward gradient learning to output 1. So this is actually increasing the learning rate for output 1. The reason we did that is in this particular competition, the metric actually counted your accuracy of this one twice as important as the other 2. So it was important to really get that one correct. So we went ahead and we emphasized.
Very cool. So this is like, because in machine learning, we often talk about weights in the context of the parameters. And so here we're using the term weights in the same way when we're talking about like a weighted average. And so I could see how there's a little confusion there, yeah.
Yes, I see. Yeah, we're weighting the importance of the head.
Someone's asking about why you started with a learning rate of 0. Did you though? I thought you had a very low learning rate, but it wasn't 0, was it?
Yeah, so we did start it at 0. Let's go ahead and look at this plot. So here's a picture of the learning rate. So in epoch 0, the learning rate is 0. In epoch 1, maybe it's 0.002, and then so you can see here it's increasing. We don't actually get to learning rate 0.001 into the 5th epoch. Now, again, this is just trial and error. You know what? If you started with a high learning rate, it still works very good. But you frequently see people do this when we're using transfer learning. The reason is you've already downloaded a net from the internet and the weights already have values. The model can already recognize certain images. So we're going to train it now on graphenes. And what happens is if you set the weight too high, sometimes you just immediately erase all of its previous training because you modify the loss is how fast you modify the weights. So by doing this gradual increase, we start from what it already knows about images, and then we slowly accustom it to the new images. And a lot of literature says that this in the end will make a more accurate model, and sometimes it does. But again, it's an experiment. You should try different ways and see what works.
That's great. Should we keep doing more questions, or if you need to go back to the training, I don't know how it's coming along.
We'll answer two more questions. We'll peek in here. Yeah, so already, wow. So look, already our leaderboard score is up to 0.873. That's nice. We've gone 17 epochs. We'll let it go. A couple more. All right, we'll answer one more question, and then we'll answer a couple more questions at the end.
So maybe there's a question about how did you efficiently experiment with kind of the resizing of the images in the pre-processing stage in terms of, I think it probably is referring to the size that you chose, the dimensions. You could choose any number, right?
Yes. Yeah, you're right. You can use any number. So they're given to you, 137 by 236. So obviously, you can just try the original image size. Don't even resize it. So you always have two things going on when you choose the resize. So I recently made a post how the resize, it's not always bigger is better. When you show your model a different size, your model sees different things. So you could be surprised. You might use a smaller size and all of a sudden your model's more accurate. So it's a bit of experimentation. But there's a second thing going on, which is when you use bigger images, it requires that your computer has more resources. For example, if you want to also have big batches, you need to be able to fit all of those that whole batch in your GPU RAM. So there's two things you have to balance here. You want to experiment with different sizes, just play around, and you'll be surprised what works and what doesn't. But you also have to kind of adjust to your specific hardware. If you have the advantage, for instance, if you have multiple GPUs at home, you can, use that strategy, wire them together. Shoot, you with 4 GPUs, you could have images that are 1,000 by 1,000 and still be doing large batch sizes. So you got to kind of balance. You want to try different ones, but you also got to sort of stay within what you can handle on your
Gotcha.
compute
And
resources.
along those lines, people are asking about whether you always train using Kaggle notebooks versus your own environment, and then kind of similar to that, how to know how many epochs to train for, right? And this kind of ties back to the resources question.
Yeah, so I could say, so I've now been competing at Kaggle for a year and a half, and I could say for my entire first year, which I won a bunch of gold medals and silvers, I worked exclusively in Kaggle notebooks. That's all I used. So Kaggle notebooks, they come with one NVIDIA P100, so it has 16 gigs of RAM. So it's sort of an older GPU. It's kind of limited in its power, but nonetheless, using just that GPU, I was able to do very well. So recently I've started working with NVIDIA, and now I have access, through the company, I have access to many GPUs. Specifically, I have access to the V100. So now I'm lucky that I could actually train with, V100s. I can even wire a couple V100s together. So this has allowed me to do a lot more than I've previously done. I can now experiment with bigger image sizes. I can train faster. And also, as we mentioned earlier, I can do more experiments. If you looked at my track record, I started working at NVIDIA a few months ago. And in the last few months, I've already won 3 gold medals. So yes, there's no denying the fact that if you have better resources, you can do more experiments faster. That's key to finding that accurate model. And you could also, it allows you to do some, things like bigger images that you couldn't.
Sounds good, Chris.
All right, well, let's hop back in and see how the model's doing here. So it's trained for 27 epochs. Wow, our leaderboard score is already over 90%. We're gonna go ahead and stop this. I'm just gonna hit stop. You'd find if you run this notebook, 150 epochs, you'll get this number actually up to 98%. And note, we're only training with 25% of the data at a very small image size. If you were to use 100% of the data and try, 128 by 128, this model can get as high as 99%. All right, so the fifth area of experimentation is post-process. So this is an often overlooked area. The reason that this is important is because frequently the competition metric, which is in this case is macro recall, loss does not automatically optimize that and make that as high as it can be. No loss is going to optimize recall. So we're going to optimize it by hand. And if you know the definition of recall, recall is the percentage of the true positives you've identified divided by the true positives that exist. So you see, you want to try to find the true positives. And furthermore, that fraction is increased most for the cases that, for the graphene roots or constants that are rare, that there's only few cases to begin with. So what we're going to do is we're going to transfer predictions from the common classes to the rare classes. So let's go ahead and load our saved model, which has been trained on 20 epochs. We're going to go ahead and predict on the validation set. As we saw earlier, that's has a macro average recall of 0.908. We're now going to move predictions from the common classes to the rare classes and reevaluate. Wow, our leaderboard score just jumped up to 0.929. Guys, this is a big secret post-process. I could tell you in many competitions, you can actually take a public notebook and you could actually do a post-process, which actually optimizes the competition metric. And many times you can turn public notebooks into silver medals. So don't forget about the post-process. So let's review what we've done today. So what we've done today is we've done one experiment. And I told you that the overall strategy is to do many, many experiments, and we want to keep a record with our log file. And you want to keep trying different things and try to get your model local validation as high as you can. We mentioned the different areas that you can experiment with. You can try different pre-process and feature engineering, different data augmentation, external data sets, different model architecture and loss, different training schedule and optimizer, and different post-process. So after you've done lots of experiments and you found your best model, that is when you then you've been saving all your models. So you can look at all of your logs and you just take, then the final step in every competition, the final step is you load in your saved model and you go ahead and you use it to predict the test set. And we'll just quickly do that. So we're loading in the test data. We're going to go ahead and predict the test set. We're going to go ahead and apply our post process to the test set. And then finally, we write a CSV file, and that's what we submit to Kaggle. And then there's the excitement. It's submitting and it's scoring, and you're waiting, and then wow, you see your leaderboard score. So that's it. I hope you enjoyed the talk. Thank you everybody for attending.
Thanks so much, Chris. That was amazing. As always, you are a master, a grandmaster, as it were. And if you like, I'm sure people would love for you to hop into the chat afterwards and take a look at any other questions that folks may have asked, and feel free to address that kind of over the time that remains, and that'll also kind of get captured into the recorded video at the end, so folks will have those answers. But yeah, for now, let's have you, unless there are questions you want to address from the live stream now in your presentation, we can have you drop out of the presentation mode, and we'll wait. Abhishek will be on with us shortly.
Okay, yeah, sure. While we're waiting, if there's a oh, okay, Abhishek's here. Welcome, Abhishek.
Yep, please carry on.
Perfect timing.
Well, I'm gonna jump to some questions, but I'll just go ahead and jump in the forums, and I'll just kind of type out some answers, and then looking forward to your talk, Abhishek.
All right.
Thank you very much.
Let's have you take over and go for it.
Okay, so yeah, I saw Chris's talk, quite amazing talk by Chris, and GPUs are awesome, obviously, but you know what's more awesome? TPUs. So in this workshop, I will be showing you how to build a framework that you can use with almost all kinds of image classification problems. And we will be using PyTorch and TPUs. Since we are limited in time, so I might rush a little bit from one place to another, but if you have any questions, feel free to ask me. And we will be building a system like a framework in such a way that you can easily switch from GPUs to TPUs using PyTorch and apply it to any kind of image classification problem. So first 15 minutes of this workshop, I will spend talking about the history of TPUs. I'm just kidding. My workshop involves a lot of coding. So if you have access to a laptop, or just fire up a Kaggle kernel and just code with me if you want. So let's start. And now you can see my screen, and this is VS Code that I generally use for making YouTube videos. So the first thing so you can see two files, dataset and engine.py. And I have already created a kernel which is empty, but there is another kernel which is not empty, and that's melanoma detection with PyTorch. So you can use that kernel as a little bit of reference if you want, but you don't have to.
Hey, Abhishek.
So the first thing
I'm going to interrupt you one moment to have you increase your resolution so that folks can see your code even more sharply. No problem.
Oh, sorry about that.
I promised I would remind you, and so here I am.
Is it better now?
Yes, it is. Great.
Okay, great. So you can take a look at this melanoma detection with PyTorch. It's a GPU kernel, but we will be using TPUs, and we will design a data loader, and we will design some kind of engine for training and validation. So let's see, let's start. You can see some of the code here. I have imported a few things. I have imported Python PIL to read the image. I have imported Torch XLA. So that's what you need when you're training your models on TPUs using PyTorch. And there is one more line: load truncated image is true. It's because some of the times images are not truncated properly, and then PIL won't read it. So first step is to create a classification data set. And in this one, what we will do, we will create it in such a way that we can just reuse it for any kind of classification data, image classification problem. So we have an init function which takes image paths, which takes targets, and takes a resize, and whether to resize or not, and augmentations. So it doesn't consist of anything else, only these things. And then I write self.image paths is image paths. So image paths is a list of strings, path to images. And we have self.targets is targets. And that's a numpy array. And then you have self.resize to resize, and that's a tuple, or it can be none. And self.augmentations is augmentations. So augmentations here comes from a library called Albumentations. I hope I'm pronouncing it well. If you have not taken a look at it, do that now. It's a quite good library for augmentations. And then I return length of the data set. And here it will just be return length of self.image paths. Okay, so, and then the get item function. So you have to be familiar with PyTorch a little bit here. And I do item, and then we can read the image here. So what we will do is we have a few lines. So I have already done it, and just to save time here, I'm pasting it, but I will be explaining it. So we open the image using PIL image. So that takes your image paths and the given item index. Then you have the targets, which is numpy array. So it extracts the targets. Then it checks if resize is not none. So that means we are resizing the image. So we take self.resize 1 and 0 and resize the image. So you might want to resize it to 64 cross 64 like Chris did. And then we have then we are converting the image to an numpy array, and then applying augmentations using albumentations. And you have the augmented image here. So we extract the augmented image, then we transpose it. So channel comes first according to PyTorch. And then we return image and targets. So now this is a dataset class that we have implemented, which can be used for any kind of image classification problem. So even if you have multi-label, multi-class image classification problem, you can just use this dataset class and it will work fine. Now, the next thing that we need to do when we're dealing with PyTorch models is to have a data loader. So we will implement the data loader as a class here. So I will say probably classification data loader. Okay, and then it will take some arguments. So we will have an init function. So it has to have the same arguments as these. So we won't be using the classification dataset directly. Plus, it will have some more arguments. Now, what are those other arguments? That will come a little bit later. So I'm just going to take all this stuff from here and paste it here. And we also have self.dataset. So I can say new variable self.dataset, which is classification data loader. And inside this, you have a lot of different things like image paths, targets. Okay, so let's take this. Okay, and now image paths will be self.image paths, right? So I will do it like this. And you have targets, you have resize, and augmentations. And all of them have this self dot in front of them. So that's your init function for classification data loader, but you have to design it in such a way that it works for CPU, for GPU and TPU, also for CPU. So I will write a function called fetch, which has self and batch size. It has number of workers, has drop last, which is always false. Not always, but by default it's false, and shuffle is true, and it has TPU equal to false for now. And that becomes your fetch function. So fetch function should return the data loader, and your data loader will be the same old torch.utils.data.data loader. Okay. And here you have self.dataset, batch size equal to self.batch size. Oh, sorry, just batch size. Let me just change the name of this variable. Okay, and then you have sampler, which is by default none. So we just keep it none for now, and drop last is same as the argument, and num workers same as the argument num workers. So the number of cores you need to process the data. So you have all this, and then you return the data loader. So we have not done anything interesting here. You could have also done it in a simple button script. So what makes it interesting is this sampler. So when you're using TPUs, you have to have a distributed data sampler, which distributes the data on all the available cores of the TPU. So I can say if TPU, then I define my sampler a little bit differently. So I can just do torch utils data dot distributed sampler. Okay. And inside that, I have some arguments. So one of the arguments is your data set. And then you have an argument called num replicas. So num replicas is the number of different cores of TPUs that you have, and it's usually 8. So we can also take it from torch XLA, and it's xm.xrt underscore world underscore size. Okay. So we have imported this here. So if it's available, it's imported. It's not available locally, so that's why I keep it in try except block. And then you have rank. So rank is the current ordinal. So xm dot get ordinal. And then in the end, you have shuffle. It's just the same as shuffle. And here, now I can replace this with sampler. So now you have designed a classification data loader for image classification problem that just works for all kinds of image classification problems or image classification data sets. Okay. So now to use it, it's quite simple. So we will come to that. But before that, you also need something called a engine.py. So you can see I already have some imports here. So the new import in this case, we have the parallel loader from Torch XLA. You need to wrap your data loader inside parallel loader for training on TPUs. And then I have also added TQDM. So you need it. You might don't even need it if it's your wish. So I just use it to track the progress of training. So now I can define a engine class. Okay, and inside that I have a train function. So the train function takes a few arguments. It takes data loader, model itself, it takes optimizer, which can be Atom or SGD or whatever you want to use. It takes the device, so that's CUDA or CPU or XLA device, and it takes a scheduler, which can be none. And then you have TPU equal to true or false. So putting it to false here. So once you have these things, you can now write your training function, which will use TPU when it's true. So if you have to write a training function which doesn't use TPU, it's quite simple, and you have already done that quite a lot. So you can just put the model in training mode, and then you can say, okay, if, I define TQDM instance. So TQDM, then I have data loader, and total here is length of the data loader. So now I go over each sample, and now I go over each sample. So for batch index and D in enumerate K0. And I transfer, first thing I do is to transfer everything to CUDA device or any device which is there. Right. So now if you look at how I have implemented the model in this kernel, you will see that the forward function has two arguments, image and targets, and that's what we will be using, the same names. And you also see that when I implemented the classification dataset class, I have image and targets, same names. So what you can do is you don't have to like go through all the, so you don't have to go through all the dataset items. So you can just do something like this for kv in data, let's call it data dot items. And here you can say data k equal to v dot to device. So you don't have to do it for each and every item inside that's coming from your data loader object. So you have that, and then you can just do something like underscore. So first thing that I do when I create a model like this in PyTorch, the first thing that's returned is the output, and second thing is always the loss. So loss is calculated inside the class. So I can do underscore comma loss is model and star data. So now I saved a lot of lines of code, and this is something that you can just reuse anywhere you want. And now what we have to do is we have to do loss dot backward, and that's quite simple. And optimizer dot step, and if scheduler is not none, then do scheduler dot step. Okay. So this is like basically it. You have to also do optimizer dot zero grad. Okay, so this is basically it. And this works for GPU. And when you're using TPUs, it's a little bit different. So the first thing that you have to do is wrap your data loader inside this parallel loader. So we will do that first. So if TPU, just write if TPU, and if that's true, then you wrap the data loader. So to wrap the data loader, it's quite simple. So you can say something like parallel loader. So I'm just using what's used very often. And okay, and I have data loader and I need the device on which it's going. So when you're training on TPUs, you're training in multiprocessing way. So if you have ever used joblib multiprocessing, it's like that. So uh, it creates a copy of all the functions. And so next thing that you do is you take tk0, which is same as your same as this one, but there's a little difference. So you have to say, instead of data loader, it's loader dot per device loader, and here is your device. Okay. Yeah, that's right. I don't have linting installed. And this comes in else now. Okay, so now we got everything. Just have to remember that this is going to print a progress for all kinds of from all the cores. So you will get 8 of them, but it's very easy to just have only one. I will leave it as an exercise for you. So now we have to do one more thing. If so loss will be calculated across all the cores individually. So you want to combine them. So you want to have some kind of function that reduces everything, all the scores from different cores. So I will just call it reduce fn, and you have values. And what it does is just returns sum of values and divide by length of values. Okay. So if TPU, then the loss is not the real loss. So it's coming from all the cores. So then you want to use the reduce function. So you can say reduced loss is some dot. So there is a mesh reduce function that you can use. And here you can say some name, loss reduced. And then you have loss and reduce function. Once you have all these things, you are all set to train your model on TPUs. But that's not it. Like, you also need to write a evaluate function. So I have written it in and put it in a small kind of library that I use from time to time. It's called, well, that's fantastic machine learning. So it's nothing but just a wrapper, like all the wrapper libraries that you have. And if you go inside there, you will see inside data loader for image classification, you have the classification data set. And it consists of everything that we just wrote. It consists a little bit more. And if you go back to engine, you will find the classification engine, or the general engine that you can use. So it has a lot more stuff than what we just did, but just to save time, I cannot show you how to implement all of them. So what it does is, like, we were here. So if you're using TPUs, and it also uses some kind of average meter, so it stores all the losses, and then in the end it returns the average loss. So we have that, and now we can try to convert our code that we wrote here to TPU. So here we have the classification loader, and we have the train data sets. We have the train data set loader, same for validation and all. So let me see. Now we have to change. We don't have to change a lot. We just have to import the stuff that we need, and we just install this library. So I'm doing it from there, and you can also write it in the kernel, but it's just going to make your code messy. Or you can use utility scripts. So now this is our training code, and training code takes a fold. So before we start, we divide the dataset into 5 different parts. I'm using a stratified k fold here, which is not advisable in this specific competition, but you can probably use it. And then you have the training function that takes a fold, and then it splits the data into training and validation fold. And then you have the device, you have the number of epochs, the batch size of training, batch size of validation, and then you load the model and send the model to the CUDA device. And you have mean and standard deviation of the ImageNet dataset. So what we are using is we are using SE-ResNext, so which is pre-trained on ImageNet dataset, and you have the augmentations, right? So the first thing that you do here is to normalize the image using the mean and standard deviation values. So these are not made up, these come from ImageNet. And then you can apply all kinds of augmentations that you want for training dataset. And you need the same thing for validation dataset. So you have the normalization function that's going to exist all the time. If you want some test time augmentations or validation time augmentations, then you can probably include those augmentations here if you want. And then we create list of training images and training targets, which is a numpy array. So, and we have a list of validation images and validation targets, which is validation targets is also a numpy array. And then we create the data loaders, right? So there will be a very small change, and you will see that how to convert when it converts to TPUs. But most of the stuff is going to remain the same. So you can use when you're creating this data loader, which is like really generalized, you can use it for any kind of classification problem, and you can switch between GPUs and TPUs. So here is our kernel, the TPU kernel now. And here we have, so this will be available on the same link right after the workshop. So one thing that you need to do is you need to install the PyTorch XLA package. So I'm always using the nightly version, so you can just choose one of the stable. So it's not stable anyways. So they're developing it continuously. They're making a lot of changes, and then I install this package that we just built, and I have EfficientNet. So here in this one, I'm using SE-ResNext, but since Chris was also using EfficientNet, I thought of using EfficientNet, and all the other competitors in this competition are also using EfficientNet anyways. And we have this base model, which is EfficientNet, which is pre-trained Efficient B0, trained on ImageNet. And then you have this, we change the output, the fully connected layer. So we have the 1280 input features and only one output feature. And in the forward function, we calculate the loss. And this part remains the same, where we create the fold. So it's created the same way. And here we define the model. So this is very important, that you don't define the model inside the training function. You define it outside the training function, because PyTorch XLA is going to make copies of it, and you will probably run out of memory if you define it inside the training function. So I just define the model here, and it's inside this multiprocessing model wrapper, which is also from Torch XLA. And then you have the training function, which is more or less the same. So what changes here is the classification loader. So I've changed it a little bit now. You can also make the same change in the old GPU kernel. So you have the classification data loader, which takes the image paths, which is a list, and all the targets, and it doesn't resize anything. So we are using the original size. We should not do that. And then you just write dot fetch, and then you have the training. You have the arguments training batch size. You have drop last equal to true. So when you're using PyTorch with TPUs, just remember to do drop last equal to true when the model is in train mode. And you can also shuffle it if you want, and TPU is true because we are training on TPUs. And then we do the same thing for validation dataset, but you have the validation batch size, and you have shuffle as false. You can make it true if you want. So we're not recording anything except the loss anyways. And then everything else remains the same. And here also everything is the same except the fact that now you have a new argument called use TPU. You add it as true, and then you are able to train this model. So I was doing some experiments, so you can just ignore this part. And whenever you train on GPUs, you need to create a multiprocessing function wrapper, and you need to spawn the processes. So these two steps will remain the same for any kind of PyTorch model which you want to train on TPUs. One thing you need to remember that whenever you use a print, it's going to print from every core of TPU. And to avoid that, you can just use the master node, and instead of print, you can just write xm.masterprint. And same here that I've written. And I tried this model, and I think I'm running out of time, so I won't be able to start training it now. This step is going to take like a couple of minutes. This step is going to take 1 minute, and the model training is going to take some time. But it's in the same setting. So the setting was 32 batch size. Now you can increase the batch size by a lot because you're using TPUs. So your model will become a lot faster. So compared to the efficient net kernels that I've seen on this competition, this thing is taking 2 minutes versus 8 minutes. So it's already 4 times faster. So you can make faster experiments. And with PyTorch, it's much easier because you can include any kind of augmentations you want. You don't have to convert the data set to so you don't have to worry about that. But you have to remember one thing: it's going to create copies. So it's nice if the images are stored somewhere, and in this case the images are stored. So there was a nice data set where this guy converted everything to 2 to 4 cross 2 to 4 images. So the images are stored in a directory. So that's nice. So don't try to load it into memory, because then your memory is going to crash. One thing that you have to remember when using PyTorch and TPUs is this memory thing, and you should always keep that in mind. And um, you should create your code in such a way that you don't use a lot of memory, because after a few epochs, and if you have a bigger model, and after a few epochs, it's going to break. And you can also use the garbage collector from Python. So I use it after every epoch. So use it like that. Don't use it in the data loader or engine .py, because then because it takes time, and your training will become slower, and you will think that TPUs are slow, but they are not. So I will share this notebook right after this workshop, working version of this. So this is the working version. And if you have any questions, I'm happy to answer. I know I've been a little bit fast, but yeah, the time was less. So thank you very much.
Thanks, Abhishek. That was amazing. We have a couple of questions coming through on the live chat and in the Q&A link. I'll just select a few, I don't know, at random-ish, depending on what kind of stuff you want to talk about. Early on, there were some questions around augmentations versus PyTorch transforms in terms of the difference between them. I think just one is just an external library, right? There's different. The difference between augmentations versus the PyTorch transforms.
Okay, for me, it's like I just find it easy to use one thing. So just choose what you want to use, and just use that. So whatever you can do, whatever you want to do in Torch transformations, you can also do it using augmentations. So I'm just using augmentations because it's much easier for me, and the code remains the same. So if I have to do it in, if I'm creating a training augmentation, I just need to add the augmentations here, and normalization and everything is
Yeah.
also possible. So it's a matter of
Preference.
choice.
Sure. And then there is a question around kind of still around these augmentations, right? They're saying there's a handful of libraries that perform augmentation on the GPU for increased speed. They give some examples like DALI, Cornea, and FastAI2. With only 2 CPU cores on Kaggle TPU notebooks, data preprocessing is often the limiting factor. So is it possible to accelerate the augmentation step using TPUs? It's an interesting angle.
Interesting question.
Yeah.
I have not tried that, but it's one thing that's definitely possible is you can use all the 8 cores individually. So what I do is instead of creating 5 folds, I create 8
Nice.
folds and train them in parallel. So you can try to do that.
That's a great
I
tip.
mean, obviously, yeah. And I have also made a public kernel on that, so probably you can take a look there.
Perfect. And there was a question about the XRT_world call. What would be the reason for that to return 1, even though there are 8 TPU workers available in the environment? They say they've hard-coded this value and they don't use the function, but would love to have it dynamically returned correctly.
Okay, I think it's XRT_world size, and I think I'm pretty sure it returns 8. So this is something that I have to check later.
Oh, that's great. And then I think some of the other questions people answered amongst themselves. What else we got? A note about normalization, but I think they discussed that. Someone wonders what you mean by transferring common classes to rare classes, and how do you choose which ones to convert?
Okay, so this is a different kind of question.
It goes back pretty early.
So it depends. So if you have rare class, how do you want to handle it? It all depends on that.
Fair enough. That's just like one technique to do it.
Yeah.
All right, that was awesome, and thank you so much to you, and of course also to Chris and everybody watching for joining us for this kind of Accelerator Power Hour. Just absolutely amazing. And if you haven't already, Kaggle has a short kind of survey to better understand kind of what you want out of these workshops. And so for those of us who are still on, please head on over to that link. We'll have them post the link again so that you can click on it and answer those questions in the survey. Let them know what you want from these types of sessions, and then they can make sure that happens, So I'll switch over our view to being the 2 of us here. So again, thanks so much for joining me, Abhishek, and thanks to Chris.
Thank you very much.
So I guess with that, we'll leave it there. There, Kaggle put up the link for the survey, so definitely fill that out. And so Abhishek will post a notebook. Please enjoy, and and Abhishek has his YouTube channel you can check out, the book that he's writing. Always busy. The live chat really loved your live coding. Were there typos? Definitely. But did the live chat catch them? They definitely did. So always they're watching. They're watching closely.
It happens. So when you're coding something that takes 1 hour and 30 minutes, it happens. But thank you very much. Thank you very much for the invitations, and I really enjoyed it, and I hope others did too. And Chris's talk was great as usual.
Awesome. All right, so we'll call it there. Thanks everybody for attending, and until next time, be safe, be well, and have a great rest of the week.